Okay, let's get going, everyone. Welcome again to this webinar on interactive computing on Alps. So as we move ever further away from traditional HPC batch job submission and more into interactive computing, there's a more and more desire to be able to use things like Jupyter notebooks, VS Code for a development environment, and also using languages other than Python in Jupyter. So we've got 3 talks today. We're going to be first talking about the Jupyter Hub deployments that we have at CSCS on our Alps vClusters. And that will be presented by me, Tim Robinson. So I'm a platform service manager here at CSCS. And then, so I'll give a sort of 10-minute introduction to Jupyter Hub. And then my colleague Sam Omlin, who's a research software engineer here at CSCS, he will talk about using Julia kernels in Jupyter Hub. So while I'll be talking mainly about Python, he'll be talking about Julia and include the GPU profiling inside Jupyter Hub. And then my other colleague, Prashant, will talk about VS Code. So I would say that one of the most common requests that we have to CSCS at the moment is, how can I set up my VS Code environment with Alps vClusters? So Prashant will talk about that. Throw your questions into the Q&A box. We will either try to answer them live, or we will save them to the end. And you can also request to ask your question live. And I think when Sam gives his presentation, he would like if everyone asks their questions spoken, make it easier for us. Okay, so let's get moving. Jupyter Hub. So Jupyter Hub at CSCS, it allows you to run Jupyter notebooks on the Alps vClusters. And we have kind of re-engineered this since the days of the old Pitstain, if you used that system. And we now have separate deployments of Jupyter Hub per vCluster. And these are accessible at the URLs that you can see here. So if you have access to the Dane.alps, then you'll have there, by virtue of that, access to jupyter-dane.cscs.ch. Likewise, if you have access to Santis, you will have access to Jupyter Santis, and for Clariden, Jupyter Clariden. And we are also adding other deployments all the time. So there'll be a deployment on the new Eiger when that's deployed on Alps. And we also have a deployment on Briston, which is another system for the machine learning platform. So if you're an HPC platform, likely you'll use Jupyter Dane or Jupyter Eiger. If you're on the weather and climate platform, then likely you will use Santis. And if you're in the machine learning platform, then likely you will want to use the Jupyter Clariden. And it could be that you have access to all of these machines. So documentation. It's been mentioned a few times that we are rejinking our documentation at CSCS. And so there's a link here to the new docs that are provided using Markdown in a MakeDocs environment. You'll get an access to a PDF of these slides, so you'll be able to click on these links later on. Now, for Jupyter Hub, the software environment is now provided by UENV. So this is a big change from beforehand. So if you are not familiar with UENV, I've put a link here to a webinar that was given by Ben Cumming approximately 1 month ago. And you can learn all about UENV. So UENV is a kind of way for you both to be able to build your applications and also to be able to access the applications that we now provide at CSCS. So we kind of moved away from Cray programming environment and modules and moved to this new development called UENV. So you'll hear this term UENV mentioned a lot of time. Recommend going to the webinar recording after this webinar and checking it out. Now with Jupyter Hub, you can, so the Jupyter Hub, the Jupyter notebook itself is provided by UENV, and then you can use your own, say, Python virtual environment by creating your own kernel. And what we'll do is we'll have a look in a demo how you can do that. And furthermore, you can also load your own UENV if you don't want to use the one that's provided by us. And so we'll see that in the Jupyter Hub spawner page. And you can click on advanced options and get access to the ability to load your own UENV. So perhaps you have a software application that you want to be available in that Jupyter environment, then it could be that you want to use your own UENV, and then you can specify that in the dialog box. We also have support for containers. So you can use container images if you don't want to use UENV. We're trying to make this thing as flexible as possible. And we have initial support for that on the Clariden system. So this is the system that's used mainly by the machine learning platform. And we might roll out this ability to use your own container images in Jupyter on other platforms as well, depending on demand. So we already have one question from Hassan Roland Nasser. What is the difference between Dane, Santis, and Clariden? So Dane is a machine. So first of all three of these are large Gracehopper-based systems on Alps. The difference is who has access to them and what they're used for. So Dane is the main system for the high-performance computing platform, so sort of general purpose HPC. Santis is a special system which is dedicated to the weather and climate community. And Clariden is a special cluster which is dedicated to predominantly Swiss AI, and we call it machine learning platform. Okay, so depending on how your project has been allocated, you will have access to one or more of these machines. Okay, but they are all have similar architecture. They're all large 4 module per node Gracehopper systems. Okay, so let's jump right in and take an example of using Jupyter. So what I'm going to do is I'm going to use Santis machine. And so what you will do is after you go to jupyter-santis.css.ch, you will need to log in. And so this is your standard single sign-on with multi-factor authentication. And then you can click Start My Server. And then you will be presented with a few options. So first of all, we have dedicated reservations to launch Jupyter Hub notebooks. And this is specified here in queue. So you can choose this dedicated queue, or you can turn off and click on standard. So generally, you should be able to work well with dedicated queue. If something doesn't work and the job doesn't launch, then try standard. Okay. Then optionally, you can choose the account. So perhaps you have multiple accounts at CSCS and you want to charge this to a specific account, which is not your default one, and you can add that detail to account. And then you can choose a job duration. I think the job duration is up to 12 hours so for interactive use. Then we have advanced options. And here you can specify an advanced reservation. So this is quite common if we have a course running and we have, say, a certain number of nodes dedicated to Jupyter. You might have to specify the reservation in this box. And then you can specify your own user UENV user environment if you wish to. So again, this is what I mentioned before. By default, we load the prog-env GNU 2411 UENV, but it could be that you want to specify your own one, so you can do that in that box. So for today, I'm going to use a reservation for Jupyter, and I'm just going to leave everything else as the defaults, and we'll launch the job. And what's happening now is this is sending a job to the compute nodes of Santis. So it's a batch job, and what we will get is a dedicated node. So 4 Gracehopper GPUs, and so no one else is on this node. It's dedicated to me at the moment. Likewise, it's dedicated to you. And you can see that the standard Jupyter Lab environment has come up. And what happens is that you're landed in your home directory, okay? So it could be that you want to get access to your Scratch directory, and because in Jupyter you can't go up the directory tree, what we can do is we can do a little trick to make a symbolic link to our Scratch directory. So I will run this cell, which just says link to my Scratch directory, and we'll call it Scratch. And then you'll see in your left-hand set of directories that there's now the Scratch directory is available. So I can click on there, and then I can see my Scratch directory. Okay. So typically, if you're a new user to Jupyter, it's probably the first thing that you want to do. As I mentioned, you've got the compute node. So you've got access to the 4 Grace hoppers. You can see that by running NVIDIA SMI, and ready to rock and roll. So next question is likely, how do I get the virtual environment that I want, or how do I get access to Python modules in general that I want? All right, so if you can see, as a user, I want to use CuPy. And so I tried to import CuPy, for example, and I see that in the kernel that I'm using at the moment, this Python 3 IPy there is no module named CuPy. So what do we do? So one way that we can get around this is to launch terminal and activate the virtual environment that I want to use. Okay, so I have a virtual environment that I call demo. And what I'll do is I'll activate that. And I'll show you that this contains CuPy. Now it's a 13.4.1, great. Now, how do I get access to this in Jupyter? What I can do is I can install a kernel, and I'll just call the kernel demo for the purposes of today. And I see that I get the error that there's no IPy kernel inside this virtual environment. So what I need to do first is to install IPy kernel. Then I'll create the kernel, and then we should be good. So simply pip install IPy kernel. Okay, we'll let that run. Because every kernel in Jupyter has to have IPy kernel inside it. Makes sense. Wait a couple of moments. So it's installing a bunch of things that are needed, basically Jupyter related. And then what we can do is we can create our kernel. And this will install the kernel in .local share Jupyter kernels, and it was called a demo. So then if we go back to our notebook, we will hopefully be able to choose from the drop-down menu shortly the demo kernel, and that will have CuPy available. So it'll just take a fraction of a moment there. Demo, select the kernel. So now you can see at the top right-hand corner, we've got demo. It has loaded and it's idle. And with any luck, we can import CuPy. And it works, okay. So it's as simple as that. You can use your virtual environment that you're probably already using. All you need to do is create a kernel from it. So ensure that IPy kernel is in your virtual environment, and then create the kernel according to the steps that I've just demonstrated. One more thing that I want to show you. When you have finished using Jupyter, go to Hub Control Panel, and then stop my server. It's very important. So that will stop your batch job in the background. So this is the way to stop. And then I mentioned that you can use your own UENV. So if you're a power user and you want to use, for example, you want to have access to a software application, for example, Quantum Espresso, What you can do here is you can type quantum, the name of the UENV, which is Quantum Espresso version 731 v3 in this case, and then you can launch Jupyter Lab again. Log file is put into your Scratch directory, capstore Scratch, and then the name, Firecrest, hash, and then a Slurm file. So if you have any issues, you can usually find what the problem is there. And then, so now what I've done is I've loaded the Quantum Espresso UENV alongside Jupyter. And you can see that I now have access to the executable, which is the Quantum Espresso. So yeah, that's pretty much it. What we really want to hear from you is requests for enhancement. So please try out Jupyter and let us know at support.cscs.ch. And yeah, put your request for enhancement, give us your feedback, and we'd love to be able to add more functionality and improve the service as you need it. Let me stop sharing now, and I'll answer any questions in the chat. Okay, so Stefano Ragnolo asks, is it possible to use Jupyter Hub with only CPU nodes on Eiger? And the answer is yes. So currently we have a Jupyter Hub on Eiger, jupyter-eiger.cscs.ch. Shortly, Eiger will be redeployed, you could say, to be a vCluster like the other vClusters. It will stay with the same node type, so it'll be x86 pure CPU nodes. And we will have a Jupyter Hub service, which is very similar to these ones. So i.e. it will use UENV. You may be able to use containers, but certainly the same way of using it, predominantly UENV, use your own virtual environments, created kernels, should be exactly the same, except that it will be CPU only. So in a nutshell, yes, we'll have exactly the same on Eiger. So it looks like there's no further questions for now. Please continue to add them to the Q&A. And now I'll hand over the mic to my colleague, Sam Omlin, who will talk about using Julia.
All right. Welcome everyone to my little part about using Julia in Jupyter Hub. I will show you basically here just how simple it is. But before I get started, I will make a little introduction about why at all you want to use Julia for HPC. It will be only a short teaser. And then I will show you how to, well, set up Julia in Jupyter Hub. And then very briefly show how to do GPU profiling using Julia in Jupyter Hub. And then I will point you to the documentation and make little conclusions. All right, so why Julia for HPC? Julia is a language in which you can write things almost or basically the same way like in Python or MATLAB, and have this interactive environment. But it has a big difference that when you run the code, you run a method, the first time it will compile it in a static fashion and afterwards reuse that compiled code in future invocations of the same method. And so here you see a function, a Julia function, and this happens to be a CUDA kernel. And so here you can see another thing that is very particular in Julia. You can write natively CUDA code. And so this function here is a CumSum function to sum up to the CumSum. And And so this function is written in standard Julia code, but it will afterwards, as it uses the CUDA package, it will be compiled down to PTX and then go, via LLM, via LLVM, it will be compiled to PTX and then go into the standard machinery of NVIDIA. And this has the benefit that you can use all the NVIDIA tools as well, which we will see later. So what's particular here, just to give one point here, you see this shuffle sync. So this is a warp level function. So you can really go to the deepest level of programming in CUDA. But in the same time, you can also use its extremely powerful meta programming to create packages that allow you to do to write domain specific languages or something like, right? Whatever you want to call it, just packages that are very focused or very suitable for a particular domain. So here, for example, we have a diffusion function on the top, the same written on the bottom, and both generate more or less the same code with more or less the same performance. Even though it's written as if it was multiple array statements, it will not store the arrays on main memory that don't have to be stored there. And then afterwards, you can call it as simple as this. And you can build your home application that way. So now after this little teaser, I get to the very simple things, how to set up Julia and Jupyter Hub. So like Tim showed already, we can use a UENV when we start a server. And so when you want to use Julia in Jupyter Hub, you have to do that. It's not optional. So you define the UENV you want to use. Has to be at least this version, because before this Jupyter view was not available, which you need to pass as well. So this is the way you start your server. Afterwards, when you get inside, you will see that there are no Julia kernels yet, despite that you have started the server with the Julia UENV. In case that you have never used Julia before, right? If you have already done that, then it will be here. But if you have never used Julia before in the Jupyter Hub, then you have to first install iJulia and at least one kernel. And you can do that, this first time installation, by simply calling install iJulia. This is something that is provided by the Julia UENV. Else this will not be available. And so it will install, like you see here. You see my mouse, by the way?
Yes.
Okay. So like you see here on my mouse pointer, it will install a normal standard kernel here, Julia 1.11, and it will install a second one inside systems here. All right, now, in the case that you have never used Julia before, then it could look like this. Julia does not exist yet at all. And so this folder is empty, and it will then install also Julia automatically. And in addition, also Julia up, the package manager for Julia itself. It's like an update manager for Julia. It allows you to manage the Julia versions, switch between them, etc., etc. And so after installation, you see it will be there. And you will have now the kernels available. And then afterwards, you select them like Tim showed you before. And of course, you will have iJulia installed. So that's basically what it does. Now, once this is done, you will want to install packages. And the way Julia is set up is a bit different from a traditional way, where we would have one Julia version with probably pre-installed packages, etc. So we have decided to do that more modern. We have, as mentioned before, this Julia app update manager that you can install yourself all the time, the latest Julia versions. And we don't pre-install any packages, but we predefine package preferences for libraries where it is important. And where is it important? It's important for MPI, CUDA, HDF5, ADS2, and also for, well, AMD on AMD systems, AMD GPU on AMD GPU systems. And why is it important? Because for these kind of packages, we want to use system installed libraries. In particular, for example, for MPI and CUDA, if you want to use CUDA-aware MPI, you need to have need to be using the system installed libraries. And so, yeah, the system installed libraries, what I refer to, are the libraries provided by the Julia UENV. And so then for you afterwards, it's enough to just say package add and the package you want to add. I did not add here MPI because you cannot use MPI inside the Jupyter. All right, so you launch that, and afterwards you will be able to check when you do CUDA version info that you actually got a local installation. So it's using this library from the UENV. And when you look at ADIOS, what it's using, you'll see it's a library inside the user environment. When you look, HDF5 is able to do parallel writing, you'll see it does. Yeah, so that was already everything. So you could see it was really very simple. You used the UENV when you start the server, and you type install iJulia, right? That's basically it. Now, GPU profiling using Julia in Jupyter Hub is pretty much as simple. So here we have a very simple function call, or well, multiples. So here, what does that do? It does create an array with one number inside on the host, on the CPU. Then afterwards, it moves it to the GPU, creates a CU array, and then it will add to all the numbers of this array, which is only one in that case, it will add 1. So this will be a kernel, which is called a broadcast kernel. Now, so when you want to profile something, you will first run it once, because the first time it will compile it. and you don't want to profile the compilation. You want to profile what it does besides the compilation. So the second time when it doesn't do any compilation anymore. So yeah, so you do the same again, and then you will get this output. And you will see host side activity and device side activity. And like I said before, so this here does this GPU broadcast kernel here. So that's really what we want, right? And you see it uses a very small amount of time, obviously, also relatively spoken. But I mean, this is a very basic example, so it's not so much about how much time it takes, but you can see that you can see all really a lot of things here. So you can see the time to launch the kernel, the time to allocate this memory here. You can see the time to copy from host to device, because as I said here, this here will be, this array is created on the host and then copied to the device. And yeah, and like I said, in the end, the kernel. So that here you can do just by default. So because here we have here the standard Julia kernel running. And if now you want to use this nice NVIDIA tool, NVIDIA Insight Systems, you will see that when you do exactly the same, right? You run it first once and then you profile. It will tell you that it's already being profiled by an external profiler. So NVIDIA Insight System. Then what it will do, it will write a file report, and it just increases them by number. So if you haven't one there, it first of all will be just report 1. And this file you can then simply download. You right click on it, you download. And afterwards, once you have that downloaded, you can start the Insight System user interface using this file. And that will immediately bring you to a view like that. The only thing that I've done here, I've zoomed in on the part where the action is happening. And so you can see here a bit the same things. You need to zoom in more. For example, if you want to see what this would be here, right? You would have to zoom in more to see afterwards the text on it. Or if you hover on it, you also see things, of course. Yeah, so you see again allocation, host to device, copy, broadcast, etc., etc. And then, so these are the CUDA API calls here. But when you want to look actually the kernels, how much time they take here of the actual thing that is happening, then you will see it's this very short piece here in the timeline. This is where the broadcast kernel is active. Right, so that was the simple example. Now, if you're not so familiar with profiling, why you ask, maybe does that really help myself? What are use cases for that? And so here it's not for within Jupyter because it is MPI. So here is a real world example. So it is a very nice way to check that when you have computations here, for example, update velocity, an update velocity kernel, which goes from here all the way to here. it's being active. And so we can see that this kernel is running the whole time while we do our MPI things, our MPI communication. So it means we have a perfect overlap of communication with computation. And important, so this is a Julia application that I'm showing you here, using CUDA and MPI. All right, then we have documentation now, a new documentation that is being finalized and published very soon. At the moment, it is still here, where you see in the title. This ETH CSCS GitHub IO CSCS docs. And so inside services, Jupyter Lab, you will find this documentation, which summarizes what I showed you before. And inside software program, programming environments, you will find documentation about Julia in general, which gives you a bit more information about how to use Julia in general on the supercomputer, or how it is done, how it is the environment is provided. So that's all from my side. So yeah, I guess I can say it's pretty much trivial how to use it. And there are two ways for GPU profiling using Julia, not only one. And Julia is certainly a great language for HPC. Yes, that would be all from my side. Do you have any questions?
So it looks like no questions in the chat. So for now, I think we'll move on with Prashant, and then can also follow up with questions in the Q&A box, and Sam could answer those at the end of Prashant's presentation if necessary. Thank you.
I hope my screen is visible to everyone.
Perfect.
Yeah. All right. So now we'll go on to the next topic, which is using Visual Studio Code for interactive computing. And this is a widely requested question from many of our users. And but why even use an integrated development environment like an IDE like VS Code? Because it's a much more intuitive and familiar user experience. It's very easy to manage files. You have a file browser that you can click. You can download files. You can drag and drop files into it. You don't need to play around with SCP or any file transfer utilities. For many people, just using the command line feels a bit dry. And the built-in editors in the command line have to be customized for them to be more usable. But Visual Studio Code comes with syntax highlighting by default. And it has many handy extensions for languages and frameworks, and also debugging. And it also has some development aids, like it has code autocomplete. It has a very nice IntelliSense autocomplete. It has code base awareness, that if you have a big complex code base, you can go across different functions. You can click through different classes and its members. And it also has GitHub Copilot integration in it, which is also quite nifty. And for many of our users, especially even those who are just running applications and want to do analysis at the end, it makes life a bit easy, because you get visual previews of your outputs, and yeah, and it's very easy to set up. So many users want it, and we'll go through some ways to set it up over here. The basic setup, I mean, I expect most of you to have already figured out how to set up your SSH and the two-factor authentication. And you have the latest SSH keys on your machine. And I mean, this is the way you set it up. If you need to have the host name Ella, and whichever of the supercomputing platforms that you are on. You can be on Santis, you can be on Eiger or Dane or Clariden, and you would have you can set up a block like this for each one of them. And once you have that, just by doing SSH and the name of the cluster, you should be able to log in without a password. It's a very simple setup. I hope most of you have done it. And we have detailed documentation on this. Once you have done this, in your VS Code installation on your computer, you need this extension called the remote SSH extension. And this is provided by Microsoft, and you can very easily install it from the marketplace inside the VS Code. In the VS Code software, you can see it on your left-hand side. Once you do this, there's one little setting that you need to do. You go to settings and just search for remote SSH, and among the extensions you will find among the extension settings you will find this setting called remote server listen on socket. For some users, the connection keeps dropping. Selecting this ensures that the connection stays persistent. And yeah, with this, it's very easy to set up, and I'll just give you a quick demo on what that looks like. So I have a VS Code instance open here. And once I go to the remote explorer here, I can see all the vClusters I've set up. I showed you how to set up Santis, but I've also set up others over here. So I will just open one for Santis. And it opens up. And now I can open a dedicated folder on it. In this case, I'm opening my home directory. And once I open my home directory, I can see, I mean, this environment maintains persistence. Like the last time I had logged into this, the files that were open will still be there. And I'm here in the terminal in my home directory. I mean, like, you can see that I'm right here. And I can browse through my files here. I mean, and I can have a bunch of files open, and when I close it and I come back to this, it reopens this the way I left. So it's really convenient. And for many people, this does a lot more than just a plain terminal login does. It helps them to be productive. But we have users who want something more than this. Like, I mean, I showed you how to connect to a cluster here. Yeah. We want users who want, we have users who want something more than this. Users also want to use all kinds of frameworks that they use to develop their software into the environment. They want to be able to access the hardware with these programming environments like CUDA. And they want to be able to debug these tools. They want the experience of having really powerful Grace Hopper hardware on their own desktop and interactively using it. So we provide ways to be able to do that as well. And many users are users of scientific packages like this, CP2K, LAMPS, GROMACS, or the Weather and Climate Code Icon, or GT4Pi, or many of these. And these software stacks are very complex because they build upon these frameworks like NVIDIA CUDA, the GCC and the GDB debugger, or Python, or Cocos, or any of these frameworks. They build upon these, and putting these packages together is not always trivial. So we don't want to keep doing that for each user and let things break. So what we have done is we have provided you highly optimized UMs, which was mentioned by Tim before. These user environments contain tested versions of of PyTorch, of CUDA, of GROMACS, of LAMPS, and many of these packages. We have packaged it for you so that you can just load it up and expect it to work out of the box at the highest of performance on our machines. Now, we also want you to be able to develop and build on top of it. So many of these UNs also have a develop view in them where you can put your custom versions of these software and also expect them to run just as well. And here I'll go through some ways to link a UENV with VS Code so that you have the experience of running this complex software stack on this hardware as though it's on your own machine. For this, we would use something called as remote tunnels. And this is a new feature in VS Code, which we have found very useful. So it allows you to connect to a remote machine like a desktop PC or a VM via a secure tunnel. So you can use it from a VS Code client anywhere, and it's really easy to set up. So this is your VS Code client on your laptop, and on the remote OS, we have the source code, the running application, and all the debuggers and the entire software stack. It's all here. But you access it from your computer as though all of this is present in your machine. So, and how to set this up? Again, we have an extension called the remote tunnels, and this is also provided by Microsoft. Very easy to install. And once you install this, you need to do a small setup on Alps. So you need to download the command line code for VS Code, for which we have provided you the URLs on the documentation. And you need to be careful which version of this you install. Like on the Grasshopper clusters, like Dane, Clariden, and Santis, we use the ARM64 because the CPUs on these are ARM-based CPUs. But on the other clusters like Eiger and Briston, we use x86 CPUs. So you need to be careful on which version you download. So once you've picked the right version and downloaded it, this will now give you an executable file, executing this command. And this executable, you want it to be accessible each time. So ensure that you export the path of this into the path environment variables. And yeah, I mean, you can add this line in your bash RC file. So, and then it's very easy to tunnel with a UN, right? You can just start a UN as we always do. And like, for example, we provide this particular UN called Programming Environment for GNU. And this contains the GCC compiler, some standard C, C++ libraries, and CUDA. So, and this with the default view provides you access to all of these so that you can program your own application on top of it. So you can just start this and you can do code tunnel and use this cluster name environment variable so that you have an identifier for your cluster. And that should work. And this should ask you which account do you want to log in with. Select your GitHub account, and with this, it will give you a secure authentication pipeline. So it will show you a URL which you will be asked to open on a browser, and that will look like this. And it will ask you to enter a code. And once you enter the code, you can authorize your Visual Studio Code software application for it. And once you do this, in your Remote Explorer window, you should be able to see a new tunnel. And that's a very simple way of getting this to run. And this will put you straight on the login node. However, many of our users also want to interactively engage with a job on the compute node. They want access to the Grasshopper hardware directly, and they want to be running their application and interact with it. Many use cases of this would be steering the simulation as it's running, interrupting, examining how it is going on, and then adding some more inputs to it and running it again. Another could be interactively working with a language model, which is running straight on the Grace Hopper hardware, on the NVIDIA GPUs. So over here, you do the same thing as before, except that you log in straight into the compute node. And after you log into the compute node using this, you start the UENV there. And, and this works too. I'll give you a very quick demo for this. I hope the live demo gods are kind to me. Okay, so here I'm on the login node of Santis. And now I will just try to get myself onto a compute node. So I just want a very short session. I want just a single node. And this is my account. And we have a dedicated reservation today for the Jupyter group, so that we get a reservation very quickly. Yeah. So I do this. And with this, I should be very soon. Yes, now you can see that I'm already on a compute node. I mean, on this particular compute node. Now I can see that. Now let me see if I have some UENVs loaded already. So I do UENV image ls. The syntax to this is very similar to Docker. So if you're familiar with Docker containers, this should be very easy to pick up. As you can see, I have a Jupyter Lab UENV here already, right? Okay, but I have not loaded this UENV yet. So I'm on a very bare bones system right now. So what do I have with me? Let me see if I have a Python with me. I have this Python. Do I have any packages for this Python? I do a pip list, and I have some very basic packages with it. All right. Now let me load up my UENV. UENV start view Jupyter, and here I have this particular Jupyter Lab UENV, which I have already downloaded. I can do this, and now I'm into the UENV itself. How do I know that I'm in the UENV now? As you can see, there are very basic Python packages here, but if I do pip list now, the list is a lot longer. I have matplotlib, I have Jupyter, I have many more things now. And this is very useful if users want to do some Python-based analysis or scripting into it. Okay, so now let me try code tunnel name. Now, it'll ask me whether I want to choose a Microsoft account or a GitHub account. I choose the GitHub one. And now it asks me to go to this URL and enter this code here. So I do that. I have a browser window here. And in this browser window, I open this. It asks me to activate this device. This is just the first time setup. So, I mean, and you can get an interactive session for up to like 4 hours, 12 hours, and you can very easily, get half a day's work or a day's work through it. So now that I have entered this code, I hit continue. Now it asks me to authorize again. I authorize this. Okay, so now I'm all set. Now I start my Visual Code Studio Code setup. If you can see here, I can open this on the browser as well. So now I can have a Visual Studio Code instance on the browser too. However, I will show you doing this with the tunnel feature over here. As you can see, there is a Santis tunnel that's running. and I will open this tunnel on this video, sorry, on this window. All right. And now I can open my home folder again. And there you go. The same persistence exists, and I'm still on the compute node that I had logged in. And I can also choose which Python interpreter I'm using. The Jupyter UENV had a newer version of Python in it. I will have access to all of this too. Yeah. So this was and in order to close it, you just do Control C, and then you are out. Ensure that you exit, because when you're on a compute node, you are charged for the compute time for this for the use of this node. So I can do exit again, and then I'm out of the UENV, and I do exit. Now I'm back to the login node. Okay. All right. Many of our users also want to bring in their own containers. They have set up their own software stack on containers, especially people from the machine learning community use this workflow quite a bit. And so we support using containers through registries like the Docker Hub, for example. And we have a custom container engine that we have built for exactly these kinds of workflows. And this container engine allows you to deploy your containers on our HPC hardware very seamlessly. To do that, you need to start off with this very simple TOML file. This TOML file looks like this. You specify the image with the appropriate tags. And over here, I'm specifying an NVIDIA NGC container. And this is one for PyTorch. And then you specify which directories you want to mount. And you specify your default work directory. And with that, you should be able to launch this the same way as before. I'll give you one more quick demo of this, just so that this also becomes very clear. And this one is with PyTorch. So, like by default, I have a very bare bones, Python setup. I have almost nothing here. Like very basic setup here. I don't have PyTorch. I don't have any of these tools, but I can do. Now I will set up the environment. I have put my TOML file over here. Sorry. And I want to do this pty bash ensures that I'm logged in. I get a bash session opened in this container. I just hope I get the reservation quickly. Yes. Now you can see that I'm on the compute node, and I'm inside this container. How do I know that I'm inside this container? I do pip list again. And there you see the list of packages is much bigger. And I have PyTorch also built into this now. So, I mean, like there is, there you see, there is Torch, and then there is a lot more built into this. Okay. So now I want to launch this container. Now I want to launch this container inside my VS Code instance. How do I do that? So I do code, tunnel, then I do the same as before. Again, the same authentication. that we need to do the first time. Okay. All right, this is authorized now, and I open a new window of VS Code. And as you can see, this tunnel is now prepared. Okay, it shows offline here. I hit refresh again. Yes, now you see this is running. So I connect it to the current window. And I can choose, say, if I want one of my Scratch directories to be mounted, I can open it in that folder. That is completely possible here. And this opens me to the previous instance where I was working. And as you can see, I'm here in this container. And yeah, all the software stack in this container is accessible here natively, including all the debuggers, including all the utilities built in. Yeah. So that was it. There's one more important point. Because I mentioned earlier that the code command line utility is different for different architectures. It's different for the ARM architecture, it's different for the x86 architecture. And some of you might be having accounts on both Eiger and one of the Grace Hopper machines. So in that case, we have this little tip where you can use this command called uname to ensure that you're on the right architecture. I will just show you what that does. So you do uname and -m, and you get the architecture of the machine you're on. I'm currently on Santis, so which is why it shows ARM here. And if I was on Eiger, it would have showed me x86. And this command allows you to create custom folders to store them. So you install both the code versions on the clusters that you use, and you put them in these folders. And based on this command, you can export the right path for them in your bash RC file. This will ensure that in the right cluster, only the right instance of the code CLI application is exposed. Yeah, that's about it from my side. And if you have any questions, please feel free to ask. Thank you.
Okay, thanks, Prashant. So it looks like we have no open questions at the moment. Oh, we do have one. Definitely running over there. Am I wrong in thinking that Jupyter Hub is similar to salloc or srun request? When I briefly use it, consume computational hours. Yes, so that is correct. So if you are using Jupyter Hub, it is a compute node that's allocated, and you are charged for the computational hours to your project.
And VS Code by default, it goes into the login node. So it's kind of like having a fancier terminal instance on the login node, basically. But as I showed in my presentation, you can also log in with Jupyter Hub directly on a compute node if you have some demanding task or some very important compilation processes running. So that will charge you the same way as Jupyter Hub does. Do we have any other open questions?
It's 7 minutes past the time, so I don't see any raised hands or questions. Many thanks to the presenters. That was a very nice presentation. So I suggest we wrap up here.
Thanks, everyone. You can always reach out to us. Our contact details, you can find them on the CSCS website for us individually, and also, of course, always submit a ticket at support.cscs.ch. for bug reports or requests for enhancement. Thanks everyone for joining.